So, welcome boys. So, this is our second video on data representation series for ISC class 11. So, last time we were discussing about decimal number system. So, here we will discuss about binary number system which we often use in computer. So, let's begin. So in binary number system, as we have already been discussed, is basically we deal with the two digits, that is 0 and 1. So that is why it is also called binary number system, because we are dealing with the two numbers 0 and 1. So first of all, we will try to know what is the need of a binary number system to design electronic circuit. So first we'll see what is the problem with the decimal number system. Okay, because a decimal number system is not convenient enough to design a digital system, because if we'll have to work with a decimal number system to design a digital circuit, then we have to work with the 10 different voltage levels, because each voltage level will denote one decimal character, and it is ranging from 0 to 9. So we have to work with the 10 different voltage levels, plus 5 millivolt or 0 millivolt or something like that. So on the other hand, so that is why it is always easy to design an accurate electronic circuit when we have to deal with only two voltage levels. Make sure that two voltage level we will have to work on. So it can be very easy, like high and low, or it can be 0 or 1, or on and off. Like we normally know, even electric switches at home, we have only two options. Either we can switch on and or off. Same way electric bulb can be in two state, on or off. So then it become very easy to work with the binary numbers, where we'll have to deal with only two numbers, 0 and 1. 0 means low voltage, whereas 1 is high voltage. Okay, or plus 5 millivolt or 0 millivolt. So that we'll discuss later in this chapter. So that is why it is very easy, and almost every digital system uses binary number system, or also called base 2 number system, whereas decimal number system is called base 10 number system, and it is called base 2 number system. So let's move to the next. Now we'll see binary number system is also a positional value system. This is also a positional value system like decimal number system. So here also position of each bit, which is actually binary digit, is most important, and each binary digit has its own value or weight expressed as a power of 2. Okay, so place to the left of the binary point, this is our binary point. Like we have decimal point and decimal number, we have binary point here for binary numbers. It's the counterpart of decimal point. Okay, so places to the left of the binary point are positive powers, whereas of 2, whereas in the right these are negative powers of 2. As you can see here, negative powers are there in the right hand side of the binary point, whereas in the left we have positive powers of 2. Okay, so we have a binary number, let's say 1010.0101. So in this case, this is 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, and 2 raised to the power 3. Whereas here it is 2 raised to the power -1, -2, -3, -4, and so on. And we have already been discussed in the decimal number system, the rightmost is called the least significant bit, because it has least significance here, whereas this leftmost has the most significance, and that is why it is called most significant bit in this given binary number. Now we will see how we can convert decimal number to binary number. Okay, so let's take an example of a particular number, let's say 43, and here I've written base 10. That means it's a binary number, its base is 10 and the number is 43. Now we need to convert it to sorry, this is decimal number 43 and we need to convert to binary, that is base 2. So we have a number called 43 which is base 10 decimal number, and we are converting it to binary number. So there's a very easy method to do this called repeated division method. So by doing repeated division method, applying this method, we can easily convert decimal number to its binary equivalent. So for this, what we do, we simply divide and keep dividing the number as long as it is not coming to 0. So here what we are doing, we are dividing 43 by 2 and storing the remainder in the right hand side. So when we divide 43 by 2, it comes to, quotient is 21, remainder is 1, then for 21 it comes 10 and the remainder is 1. Okay, then when we are dividing 10, then it comes 5 and remainder is 0, and for 5 quotient is 2, remainder is 1, and for 2 it is quotient is 1 and remainder is 0, and lastly 1 is left, will be taken as it is. So by repeated division method, we see we have got these remainders, which we have written here in the right hand side. Now here we'll have to keep this thing very clear, is that the first remainder which was on the top is the least significant, whereas which is at the bottom is called the most significant bit. So while writing, we'll write in this order, as clearly shown with the arrow from bottom to top. So while writing these remainders, make sure that you are following from the bottom to top approach. So that is why we are writing as 1 0 1 0 1 1. Look at the 1 0 1 0 1 1. So here I have written 1 0 1 0 1 1. So this binary number, or a combination of these binary digits, is binary equivalent of 43. Okay, so this is binary equivalent of decimal number 43. Now in the next slide we will check our previous answer, or at the same time we can say we will convert now binary number to its decimal equivalent. So what we are doing here, we are converting now binary to decimal. This can be another problem, but here we will cross check our answer also. So in the previous example, we got one binary number called 101011, which was base 2. Now we'll convert it back to the decimal and see whether our answer is correct or not. At the same time, we will convert a binary number to a decimal equivalent. So for this, it's quite easy. First, we'll have to write down all these binary digits like this: 1 0 1 0 1 1. Now what we will do, because of it's a positional value system and that is it is base 2, what we'll do, we will multiply each bit by 2. We will multiply each bit by 2 and then the power, and the power is nothing but its position. And if you see the position is like 0 1 2 3 4 and 5. So what we are doing here is, here I have 1, so I will multiply 1 by 2 raised to the power 5 plus 0 multiplied by 2 raised to the power, sorry I left out here, that is 4. Okay, and then 1 multiplied by 2 raised to the power 3, then plus 0 multiplied by 2 raised to the power 2 plus 1 multiplied by 2 raised to the power 1, and then finally 1 multiplied by 2 raised to the power 0. Okay, so as you can see, I have multiplied each bit by 2 and putting the power as 0 1 2 3 4 and then 5. Then now simplify it. Okay, that is quite easy. 2 raised to the power 5 is 32. 32 multiplied by 1 is 32, and any number multiplied by 0 is 0. Then that you can straight away leave out. Then 2 raised to the power 3 is 8. Then again 2 raised to the power 2 whatever is multiplied by 0 is 0. Then 2 raised to the power 2 is 2. 2 multiplied by 1 is 2, and then 2 raised to the power 0. So any number raised to the power 0 is 1. 1 multiplied by 1 is 1. Now you just do the sum. 32 plus 8 plus 2 plus 1 will again give us 43. So as you can see, in the previous example we were converting a binary number to a decimal number to binary. Here what we have done, we have converted binary number to decimal and we have got the same answer again. So if the total is 43, so it means 101011 base 2, that is decimal number, is equivalent to binary number is decimal equivalent is 43. So in this video we have seen how we can convert decimal number to binary number and now binary to decimal. So these two methods are quite common and quite easy to work with. So here I end my video. Thank you very much.